I want you to try an experiment. I want you to put a stack of books on the desktop and then start to push ever so slightly against those books. And let me give you an idea of how hard to push. I want you to start out by pushing with a force of maybe about 1 Newton. Now, a Newton is less than a pound. I think this would be about right. A Newton is a little bit less than a quarter pound, but a little bit more than 1/5 of a pound. Somewhere in there, right? Somewhere just a little less than a quarter pound is a Newton of force. So push with 1 Newton of force against the stack of books and notice what happens. It probably stays at rest, right? It's probably in static equilibrium even as you're pushing it. And let's think about a free body diagram here. Let me draw a dot off to the left. That represents the stack of books. So without you pushing on it, it's in equilibrium because the downward force of gravity is offset or canceled by the upward normal force, so the net force is 0. If you push to the right, you should expect for it to accelerate to the right, but obviously some force shows up to the left to keep it at rest. So we say the force to the right, we'll call that F applied. That's how hard you're pushing with your finger. And of course the force acting back to the left is friction. We'll symbolize friction with lowercase f. Now I want you to push with 2 Newtons of force. See what happens. The stack still stays at rest, doesn't it? So you make the applied force a little bit larger, and what happens? Well, the friction force becomes just large enough. So the friction force can vary. It can grow to match how hard your applied force is. But as you push with 2 Newtons, 3 Newtons, 4 Newtons, 5 Newtons, as you continue to push, this increase in your applied force corresponding to a matching increase in frictional force only reaches some limit before finally you break what we call the static friction that can keep the books at rest, and now the books will start to slide. And then a whole different type of friction takes over, known as kinetic friction, the friction that governs the behavior of the books when they're in motion. And in that case, you could have a free body diagram that looks like this. The frictional force will have grown to its greatest value and then remain constant from there on out. Once the friction reaches the kinetic range, it now has a constant value regardless of how hard your applied force is. So you can have an applied force that's greater in magnitude than the constant kinetic friction. We might say F subscript K for kinetic, where here we add an F subscript S for static. Yeah, if these two are out of balance, then there's a net amount of force pointing to the right, and the books can accelerate. Of course, you could back off your applied force so that it perfectly matches the amount of constant kinetic friction, and at that point, what happens? You might be tempted to say the books stop again, but I believe if you've already broken the static friction, got it to slide, and then decrease your push until it matches the kinetic friction, it doesn't mean the books are at rest. It means the way in which they're sliding is with a constant speed. So bottom line is, if the net force is non-zero, they accelerate, and if the net force is 0, then the books are in equilibrium. Equilibrium could be static equilibrium, or it could be a dynamic equilibrium, in which the books are moving at a constant speed. So we can formally do this experiment a little more clearly. If I take a wood block and attach a scale to it, so it gives me a reading as I pull with increasing force to the right, we could plot some data points. I can say, what happens if I compare my applied force in newtons to the resulting frictional force? Well, if I pull and the scale reads 1 Newton, and I see the block remains at rest, then I know the frictional force is also 1 Newton. So I have a data point where 1 Newton of applied force corresponds to exactly 1 Newton of frictional force to keep it in a state of static equilibrium. And likewise, 2 Newtons and 2 Newtons. And on it goes. Well, you think then that you're going to create a graph that just indefinitely grows with a slope of 1. But ultimately, what's going to happen, we see the scale is going to reach some maximum value for which the block remains at rest. And at some point, the scale is going to tip out at the greatest reading it can achieve, and all of a sudden that static friction is broken and the block begins to slide. So some maximum value is reached. We'll call that F max, lowercase f for friction, maximum value. And then if I continue to apply even more force beyond that threshold for which the maximum friction has been achieved and the block begins to slide, you notice that while it's sliding, the reading in the scale is going to slightly back off from its greatest tipping point. So it maybe points here now. In other words, the frictional force drops down a little bit and then levels off to a constant value once I reach the point where the block is sliding. For all the forces that I applied prior to that, the block was at rest. So we have two conditions: a static condition in which the force can vary anywhere from 0 up to some maximum value. And then we have a second case, sliding. And in that case, the frictional force is something lower than the maximum value and remains constant regardless of how much applied force I give. So we say there's a difference between static friction and kinetic friction. Static friction varies, kinetic friction is constant. The maximum value of static friction is greater than the constant value of sliding friction. Now, I didn't learn this from an experiment of attaching a scale to a wooden block and pulling on it. I actually learned this at a pretty young age, but maybe not with that exact language. So I had been on a ski trip with my family. I was probably, well, I can't tell you exactly how old. I'm going to guess I was about 10 or 11 years old. The reason I think that is because I was at that age where I was old enough to venture out on my own and get into trouble, but not savvy enough necessarily to figure out how to get myself out of trouble. So there were these apartment buildings that we'd often walk between. I'm going to remove myself from here for a moment because it didn't really look exactly like this. It had snowed so much that it had piled up on the roofs, and it even piled up quite a bit in between the buildings. In fact, there was so much snow we couldn't go skiing because it was too much for them to be able to groom. So for the first few days of our trip, I got really bored. I couldn't just sit around in the condominium. So I'd ventured out here and realized this is almost close enough for me to be able to climb up on top of the roof. And sure enough, I would just about make it up there. I would start to climb up, and actually I think I was wearing like a puffy sort of ski suit, right? This nylon outfit that was pretty smooth relative to the snow. And I'd climb up and immediately just fly back off, and it wasn't too far to fall, so I didn't get hurt. And I'd try to climb up again, and I kept doing this till finally I found a way, if I sort of dug my hands in, I could get up here, and I found myself past the apex of the roof. Now there was a problem with this because when I looked over the other side, I realized that the snow hadn't built up in the same way, right? Because the path between the buildings was narrow enough, the snow could pile up. But over here, and another thing, there's kind of a hillside. So the snow really didn't pile up so much over here. And if I remember right, there was a fence along this walkway. And so I looked down and saw it was pretty long drop. So I got really scared. And thank goodness there was one of those pipes that come out through the roof of the house for venting. Actually, we're going to find out in a future unit of study when we're studying fluids why there has to be at least some pipes coming out of the roof of your house. It has to do with the way in which wastewater flows. Anyhow, I held onto this pipe and it kept me safe. I didn't go sliding off just because I had something to hold on to, but then I would sort of test my fate, test my nerve, and where my hands were holding on this pipe, I'd let go for a moment and then really quickly grab hold again. And then I'd let go a little longer. And I found that if I let go, I wasn't sliding anymore. Now, I didn't understand how this could happen, right? When I first reached the apex, I was sliding. I was on my way to flying off when I grabbed that pipe, and it brought me to rest. Well, what happened was something known as frictional welding, okay? What if we were to zoom in on the surface of, so I'm modeling myself like a block and the roof like a perfect incline, right? So we got a block sitting on an inclined plane, and that's sort of what we have with me sitting on top of this roof. Well, we zoom in where the two surfaces meet, where the bottom of the block meets the surface of the incline. And what we'd find there is that the surfaces might look smooth and even feel smooth to the touch, but if we start to get down toward the microscopic level, we'd see that there's a certain unevenness to both surfaces. So we've got the bottom of the block and the incline. And generally what happens if you let something come to rest, or even better if you like push down and give something a bit of a jiggle and try to firmly stick it. You might do this anytime you walk on uneven pavement. When you plant your foot, you might give it a hard press and a little bit of twist. And what that does, it kind of forces the little peaks and valleys to match up. So the uneven parts can fit together, sort of like puzzle pieces. And that creates a kind of a locking mechanism, which means you'd have to tilt this ramp to a pretty steep incline before there was enough force to cause the pieces to unlock. So this is what happened. I had sat there for long enough that some frictional welding had taken place. And so a static form of friction was holding me in place. Well, I didn't realize that static friction is always stronger than kinetic friction. I didn't realize that the maximum value of friction in the static range has a peak value that's always a little bit greater than the constant value of kinetic friction. So what did I do? Well, thinking I was now safe, that somehow there was enough friction to keep me from sliding, I let go of the pipe, and then I started to swivel my butt around so I could turn around and try to walk this way to the safe side of the roof. And by doing so, I forcefully unlocked this frictional welding, and then the little peaks and valleys and bumps can slide. The bottom of the block, or the bottom of me, can slide that way relative to the stationary incline. And sure enough, there was not a strong enough value of kinetic friction to keep me from sliding off. And I did. I flew off this roof. Now, I remember this in part because I always mention this story when illustrating the difference between kinetic and static friction. But also, I always remembered these trips to the mountains. They were a fun time in my childhood. But I tell you what, I have no recorded memory whatsoever in my brain of this period of my life where I was in free fall. I just don't remember it. I freaked out or blacked out. And all I remember is I sort of came to. It could have been 10 seconds later. It could have been 5 minutes later. I don't know. But I was all tangled up in this fence down below. And fortunate for me, no broken bones, no major injury, maybe just a little bruised. It was, I believe, that padded ski suit that had saved me. So it was a very stern lesson in the difference between static and kinetic friction at a young age. And it didn't hit me until later when I was in a physics course that I had the language to describe it. In my first physics course, we did an experiment where we tried to make a measurement of static friction versus kinetic friction. And the experiment went something like this. Very carefully and very gently take an incline with an object already placed on it and start to raise the incline higher and higher and higher until you find the maximum angle for which the object can stay at rest. If you find that value, we'll call it theta max, comma, S for static. Okay. If you lift it any higher than that, you break the frictional welding. The peaks and valleys don't line up like puzzle pieces, and instead all the little peaks bounce across each other, and the object starts to move. Well, if you do that, if you get past this maximum safe angle to keep it at rest and it starts to move, it's guaranteed going to accelerate, not move with constant velocity. So what you find is you have to back off. You have to reduce the angle in order for the block to continue to move down the ramp at a constant speed. If you kept the angle the same as the maximum static angle, the motion would be acceleration. If you reduce it a little bit, and so we find theta, what should we say? Theta constant speed, all right? Theta constant speed is always less than theta max static. We'll derive in another lesson how you can determine something known as what's called the coefficient of friction. So force of friction is one thing. That shows up in free body diagrams. In fact, if we want to make a free body diagram for the block that slides at a constant speed, we know what that looks like. A normal force points this way. A component of gravity, mg cosine theta, points in this direction. The other component of gravity points parallel to the incline. That's mg sine theta. If the speed is constant, that means acceleration is zero, which means the net force is zero, which implies equilibrium. Not static equilibrium, because it's in motion, the sort of equilibrium you have when something moves at a constant speed. So all the forces cancel one another out, and this force back in this direction is F. Okay, so that's force of friction. It would be measured in newtons like any other force. But there's another quantity we think of when we talk about friction. It's not a force of friction, it's called the coefficient of friction. Often, coefficients are numerical quantities that don't have any units of measurement. It just means when the numerical value is large, there's a lot of it, and when it's small, there isn't much. So there's a coefficient of friction for things like metal on ice. And that coefficient of friction is just a pure number, and my guess is it's pretty low. There's also a coefficient of friction of maybe, how about rubber on dry asphalt? That one's probably fairly high. There's probably a coefficient of friction of wood on sandpaper. That one's pretty high. I think a coefficient of friction of, I hope, cartilage on cartilage is low. Maybe lubricated cartilage on lubricated cartilage. A lot of the joints in our body are synovial joints. In a synovial joint, there are these little sacks full of nature's, the body's WD-40, so to speak, right? We have our own lubricating fluids in these bursae. And they provide the lubrication to keep the cartilage kind of wet. So in a synovial joint where cartilage rubs up against cartilage, if the bursa become inflamed, you can get bursitis. Anything itis means inflamed, right? And if the bursitis is severe enough, then it clogs up those pores and it can't lubricate the synovial joint, and it becomes very painful because dry cartilage on dry cartilage has a pretty high coefficient of friction, and so any attempt to move causes this painful rubbing in those joints. In a future video lesson, we'll get into more detail and provide some numerical values for coefficient of friction and give a symbol for it. But I want to leave you with this idea that let me give you a symbol for it now. We use the Greek letter mu. It looks like the letter U, except it has a big dangly coming off of it, right? So it's kind of like how the Greek letter omega kind of looks like a W in our alphabet. So we got the Greek alphabet in our alphabet. Omega is not the same thing as W, and the same thing, mu, is not the same thing as U. Okay, so mu is our symbol for coefficient of friction, and there's a coefficient of static friction that describes how smooth or how rough two materials are that meet up and are held at rest, whether it's metal on ice or rubber on asphalt or cartilage on cartilage. And there's also a coefficient of kinetic friction that describes the roughness involved as those surfaces slide against each other. And the coefficient of static friction turns out is always greater than or equal to the coefficient of kinetic friction, which gives, I suppose, a mathematical reason of why the maximum static force is greater than the constant sliding force of friction. the equal, right? I get greater than. What about the equal? There are some special cases where there's no distinction between the static and kinetic friction. Frictional welding can't take place for materials like this, and I suppose that graph would look like this. As you apply more and more force, yet an object stays at rest, the frictional force grows with your applied force, and then once it starts to slide, it actually doesn't drop off. It just stays level at that maximum value. And one example I know of is Teflon. Teflon's a surface that they coat our cookware with so that the eggs can slide out easily, right? A really good Teflon pan doesn't allow for any frictional welding, and the coefficient of static friction for fried egg on Teflon is the same numerical value as the coefficient of kinetic friction for fried egg on Teflon. But for just about every other material that I can think of, the coefficient of friction in the static range is always greater than that of the kinetic range. Okay, so thanks for watching, and stay tuned for more about frictional forces.